Good evening, class. I'm actually re-recording this video because I realized first time I recorded it I was not wearing my microphone, so there is no sound with the original one. So I apologize for that. This is the retake. We'll try to make it work a little bit better this time. So in this game we are basically looking at linear dynamics, so the movement of an object over time. And to kind of get us set up, we have this starter project, which is kind of set up like the old lunar lander game, if you remember that game. If we run this, we have a lunar lander, which we're going to move with linear dynamics in a fairly realistic manner and actually implement the physics that would make this emulate the way it would work in the real world. So let's take a look at what we have. We have a lander sprite. This should be fairly similar to what you've seen before. We load content with it, we update it every time through the game loop, and we draw it every time through the game loop. So nothing we haven't seen before. When we create it, we've got a texture and a position. We set it to be in that upper left-hand side of the screen. We set our texture, we update its position, and we draw it. Now, with linear dynamics, in a 2D game, we represent the different values we work with as vectors, so vector 2's. So we have the position. We would also have a velocity vector, and then also an acceleration vector. Now the way that we're working with this game, we'll deal with acceleration a little bit differently than actually declaring a global or a class level vector for it, but we are going to do velocity. One of the other nice things about working in 2D and working with the vectors is that we can actually do the calculations for the components separately. So we can actually isolate them and look at them in isolation. So we can look at horizontal movement completely separately from vertical movement. So we're going to start with the horizontal movement because that's actually the simplest. And in this game we want our lander to start on one side of the screen and just travel to the other side of the screen. So we're not applying any new forces to it, it's just moving at a constant velocity. So we'll go ahead and create a velocity vector, and we'll go ahead and set 10 in the x component and 0 in the y. So we're just worrying about this x component right now. And then if we come down to our update, we can update our position. And the position or the velocity, what that actually means in terms of game time, or how a game functions, or the physics of it, is it's a rate of change in position. So the velocity is the rate of change in the position over time. So we need a time variable, and to make this a little bit easier than we've dealt with in the past, we'll go ahead and just create a float variable called t, or delta t, which is the change in time, or the amount of time. And we'll take our game time, we'll pull out the elapsed game time, total seconds. And of course we have to cast this. Now we could use this variable directly, but I find once we start doing more complex calculations, it's handy to just have it in that little float t. So we can take this position and then add to it, or take position not plus the velocity times the time. So we can take that velocity vector times the amount of time that's passed, and that we add back in. Now this is the equivalent of the, if you remember your equations of motion, p equals p naught, which is what the plus equal gives us, p naught plus velocity times time. So that's if we have constant or no if we have no acceleration, there's no change in our velocity. If we have a constant velocity, this is all we need. Now if we had a change in velocity, we do plus 1/2 at squared. Except we don't actually have to, and we'll come back to that here in a minute. But if we run this, because we're changing the position in terms of that velocity, and that velocity is constant, we should see that lunar lander now move across the screen at a constant speed. So we've actually got that accomplished. Now let's talk about acceleration. So we have acceleration in this game because of gravity. Gravity is constantly pulling this lander down towards the lunar surface. So if we were to create an acceleration vector, we would go ahead and add to that acceleration vector, or set that to be the vector pulling the ship down. So let's do a new vector 2, and let's make this 0 and 50, because remember, positive y is downward. So this is going to pull our ship down at a constant acceleration of 50 pixels per second squared. So this is an acceleration vector. And then to apply our acceleration, we'd say velocity, because remember, acceleration is a change in velocity, equals the acceleration times the time. And the beauty of this, we could have done it down here with the plus and then the squaring and all that, but we don't have to. And the reason we don't have to is if we think about how big this t is, this is very small snippets of time. Remember, 1/30th of the second or 1/60th of the second. So in that very small segment of time, we can treat this acceleration and this velocity as though they were constant values. So we can calculate their value at that moment in time and then apply it to the next value down. So we apply the acceleration for the amount of time to the velocity, and we apply the velocity over that time to the position. And that's really the heart of it. This is actually what calculus is. If you really get to understand calculus, it's all about breaking these big functions down into tiny pieces and then putting those back together to either derive or integrate over time. So that's really what we're looking at, is changes over time or some other variable. But this is actually, because we're simulating and we actually have this very small time step, we can just do this very simple implementation. Now if we do this and run this, we'll see that our lunar lander is going to start moving downward, and notice it's accelerating. It gets faster and faster the further across the screen we get. So that is acceleration in the downward direction. Maybe we'll crank it down just a bit. And we could actually calculate what this should be. We could say each pixel's a foot, and we could calculate how much acceleration we should see due to gravity of the moon or whatever planetoid we're trying to land on. But we can play with that and kind of figure that out. Or we can do what most game developers do and just plug in values till we find something that feels reasonable and just run with that. So it depends on how much you're wanting to have scientific accuracy in your simulation versus how much you're just looking for a fun kind of game to play. Alright, so that's our acceleration in a downward direction, but now we want to add acceleration also when the rocket of this lunar lander is firing. And in these lunar landers, that rocket was always mounted directly beneath the center of gravity of the lander, which means we don't have to deal with torque or angular motion, angular dynamics. We're going to talk about those in the next video. So if we don't have to deal with that, that's a lot easier. So we'll actually tie this acceleration upwards, or the firing of our rocket, to a keyboard key, and we're going to use keys.space here. So if we are pressing the space bar, that means we're firing that big rocket underneath that ship, and we should be adding an acceleration in the opposite direction. So we take our acceleration vector and we're going to add to it, or in this, plus equals a new vector in the opposite direction of this vector, so it needs to be negative. So we'll make this maybe negative 50 is how much thrust we'll get out of that rocket. So that is pushing us in the opposite direction. So notice this will actually cancel out, plus add 20 pixels per second squared in the opposite direction when we're firing this thruster. So now if we run this again, we're falling, we start accelerating downward, we fire our thruster, we're holding it, start moving back upward, we let go of our thruster, we start falling again, and we start accelerating upward again, and we can play with this until we get ourselves to that landing zone. And basically what you do in a game like this, or at least the goal of lunar lander, is to land safely. So you'd look at the velocity in the y direction when you actually contact the ground and decide, were they moving too fast? Did they smash into the ground, or did they gently land? And that's how you determine if you win or lose the game. But that's basically all there is to linear dynamics. We just calculate our acceleration, which is a sum of all the forces that are acting on us in that instant of time. We add that to the velocity and scale it by the amount of time of the time step, and then we take that velocity and we scale it by the time step and apply that to position. And that's really all there is to it. Now you might be wondering where we get this acceleration from. Remember the equation, force equals mass times acceleration. So the acceleration is basically the amount of force we're applying in this moment divided by the mass of the object, and in this case we can treat that as a constant because our ship's not changing mass, and our force that we're getting out of the rocket we're treating as being constant as well. So in the moment that we're firing that rocket, or the t moments, if you will, however long that t variable lasts, that's how much acceleration we're applying. In more complex simulations, we might have to account for a changing amount of mass. So if the mass is actually being used up, like technically it would be here because we're firing off our rocket fuel, so we're actually losing mass as we're firing our rockets, which means our ship is lighter, which means the amount of acceleration we're getting is basically growing because we're applying the same force on a lighter object. Suddenly that starts getting a little more involved. We don't usually go into that level of detail with a video game because we don't need to. If we're doing a true scientific simulation, if you're really trying to capture that sense of complexity, then you might want to actually think about those things and actually plug in more realistic numbers than the ones we've used here. But this is definitely enough to get us to playing a reasonable game. And you'll notice too, the same mechanic, it's very similar to some other games you may have seen, Flappy Bird for example. Basically the same mechanic, the only difference is instead of allowing you to continuously apply that thrust, it's just instantaneous. You tap the button, he flaps and adds some either velocity or applies some acceleration for a short duration that is basically impulse or immediate application of force that just lasts for a fraction of a second. So there's lots of things we can do just extending this idea of linear dynamics. And of course there's the whole other dimension where we start thinking about angular dynamics and actually how things might rotate based on where and how they're impacted by forces. So we'll actually take a look at that next time.